The title of my talk is Integration of Functional Nanoscale Vias with LAO STO heterostructures. The motivation of our research starts from the second quantum revolution, which is based on the utilization of interesting quantum phenomena such as entanglement and superposition, and aims to develop revolutionary quantum technologies like quantum simulators and quantum computers. This requires continuous search for new quantum materials with properties that meet the stringent requirements of these quantum applications, among which are programmability and coherent control of electrons. One of the interesting quantum material platforms that show a high degree of programmability is LAO-STO heterostructures, which exhibits a high mobility 2D electron gas at the interface that comes with a locally switchable metal insulator transition. One method that can be used to program nanostructures at the interface is conductive AFM lithography. We first create metal electrodes that contact the interface. Then we use a conductive AFM tip that's biased with respect to the interface to sketch the device around. And what happened is that wherever the tip touches the surface underneath, the surface becomes locally conductive. And this is reversible in the sense that we can change the sign of the voltage and reverse back to an insulating phase. Using this technique, we can create lots of interesting quantum devices with very high spatial resolution. One of the most interesting electronic devices that can be created with this method is electron waveguides, which exhibits transport in the ballistic regime with mean free path that's larger than the dimension of the device. Also shows well-resolved electronic state subbands with a fully span polarized ground state. One of the main challenges in integrating this system with other quantum materials is that LAO is a wide bandgap semiconductor, so any material that will be placed on the surface will only be weakly coupled to the 2D electron gas. To improve coupling through direct contact, we propose creating nanoscale vias where we etch the lanthanum aluminate layer to allow direct contact with the interface. We can create these nanovias with sub 50 nanometer resolution. The method we use to create these nanovias is low voltage EBL, which comes with merits and limitations. The advantage over the conventional EBL is that highly accelerated electrons that stop in the substrate cause non-redeemable mechanical and electronic damage, and this helps in avoiding this. However, low acceleration voltage limits the usable charge dose to small values due to the increase in the scattering cross-section compared to high acceleration voltage. Following the E-beam patterning, we use argon ion milling to etch the lanthanum aluminate. The question becomes, are the nanovias small enough to allow for direct contact with the 2DEG? To address this, we use conductive atomic force microscopy. In this experiment, we're sourcing AC voltage from the AFM tip while scanning a line across one of the nanovias. The acquired signal matches the profile of the nanovia, confirming that it's only coming from this region. So how can we make use of these nanovias? One direction that we're interested in is doing transport measurements on graphene nanoribbons. We have a separate talk about this if you're interested in learning more. Another direction is studying chirality of molecules in nanovias coupled to electron waveguides. We're interested in this to help understand the chiral-induced spin selectivity effect for electrons, velocity, and molecules in enantiometric form are thought to be controlling factors for determining the preferred spin state during conduction. Last but not least, in studying normal superconducting nanoislands. What makes these systems interesting is that they offer tunable realization of 2D superconductivity, which can help answer open questions about the nature of 2D superconductivity. It was observed that arrays of superconducting niobium grown on top of gold substrates undergo a drop in resistance as temperature is lowered in 2 steps. The higher temperature transition is associated with phase coherence among different grains within the same island, while the lower T drop is associated with phase locking across the array. They study the effect of varying the inter-island spacing on T1 and observed that T1 approaches 0 for a finite island spacing. This counts as evidence to the existence of zero temperature metallic states, which has been predicted to exist but not observed before. In this direction, we place a superconducting material, namely niobium titanium nitride, which has bulk Tc of 15 Kelvin inside the nanovias. This is done using sputtering following the ion milling step. The idea here is that we can create reconfigurable links between the individual superconducting nanoions on the same device. By doing this, we can study the effect of changing the Josephson coupling on the transport behavior of the superconducting array on the same sample. The preliminary NBTIN device we created, which involved turning the whole substrate into the conducting state, did not show a superconducting transition in the same temperature range as a thin film of NBTIN would do. We attribute this to the possibility of a Schottky barrier emerging between the 2DEG and the superconductor. This could be the case because sputtering and ion milling take place in 2 different instruments. One potential fix that we are currently testing is to add an intermediate titanium layer following the ion milling and before the sputtering. A similar complex oxide heterostructure system that acquired lots of attention recently is the interface between LAO and KTO. It exhibits a similar metal insulator transition to LAO STO. However, it shows a stronger spin orbit coupling and nearly 1 order of magnitude higher in superconducting TC, which might make it more desirable candidate for certain applications. Based on that, we have recently started to investigate a very similar approach to the same problem. Here we create arrays of weakly coupled superconducting islands by directly patterning the device with CAFM lithography. The advantage here is that we can avoid the lift-off procedure, and there is no chance for a barrier to occur. The data from the first device shows very interesting behavior with lots of fine structure that requires much slower magnetic field sweeping than that was feasible during this experiment. But it's quite sufficient to show that it's possible to create Josephson junction arrays. We are interested in investigating some of the outstanding questions about 2D metal phase in between the insulating and the superconducting phase. This can be achieved by backgating the same device to operate in the different regimes. To summarize, LAO-STO heterointerface is a promising reconfigurable quantum nanoelectronics platform that is suitable for many quantum applications. Improved coupling to other quantum materials can be achieved by etching lanthanum aluminate in small windows. Direct contact to the 2D electron gas can be demonstrated using conductive AFM lithography. We're interested in many applications of this method, including reconfigurable superconducting nano-islands on LAO-STO. Finally, we are interested in creating arrays of Josephson junctions in LAO-KTO and using them to probe questions about the nature of superconductivity in 2 dimensions.